In previous lecture, we studied for London equation to describe the superconducting state, and the main point of the London equation is that the electric field is time derivative for the lambda Js. Js is the superconducting current density. Here is lambda is m over NSE square, and the magnetic field is that negative called Js. And from this relation and some electrodynamics calculation, the result is that the magnetic field has this kind of Laplacian equation. Laplacian B is that lambda L square B. Here lambda L is a penetration depth, and the penetration depth can be write down as the m over mu 0 NSE square to the 1/2. And from this relation, and the gamma is the mu 0 lambda L square. And this is a penetration depth. Yeah, here. And in this class, I will talk about the intermediate state of the type 1 superconductor, and it is based on the London equation. Intermediate state. Intermediate state of type 1 superconductor. From this London equation, we know that the magnetic field decreases exponentially into the interior of the bulk superconductor. And here the solution in one-dimensional solution is that B0 is the magnetic field in the outside sample, and the magnetic field is exponentially decreases minus x over lambda L. Lambda L is penetration depth, and the superconducting magnetic field decreases exponentially, and lambda L is the characteristic length scale to penetrate the magnetic field inside a sample. In theoretical calculation from this London equation, we in many cases penetration depth is order of 200 angstrom. In typical classic metallic semiconductor, and this is a theoretical London equation. But in experiments, we many metallic materials show that 500 angstrom, 50 nanometer, and for pure metals, metallic superconductor, and in experiment, that is at very low temperature. The theoretical discrepancy, between the theory and experiment is due to the non-local effect. Non-local effect, the discrepancy is coming from the non-local effect. Discrepancy between theory and experiment is due to the non-local effect. What is the non-local effect? And London theory is the local theory, and the superelectron has a localized at certain point, and when there is basically superelectrons should have the Bose condensation in many cases, and the spin up and spin down coupled with each other, and anyway we call it as a superelectrons. And the superelectrons are at the certain points. For example, it is R point. At this R point, and the superelectron is definitely. Anyway, then in quantum mechanics, electron is not a particle but wave, but in classical point of view, and the electron can be regarded as a particle, and the particle is a local, very local entity. But in supernature, when we will see that the Cooper pair in BCS theory, and the superelectrons have a formation of the spin up and down coupled with each other. And anyway, in the from London theory, this coupling of the superelectrons is a local entity, but in BCS theory, when other Ginzburg-Landau theory, Ginzburg-Landau theory is a phenomenological theory, but in the BCS theory is a microscopic theory. And anyway, then the Cooper pairing, we call it as Cooper pair, and I will say about the concept of Cooper pair. And basically, you know that the Cooper pair is the singlet condensation of the two electrons of spin 1 and the other spin down. And total spin is 0. And there is some mediate and some anyway, it is a phonon. I will describe later. And anyway, in this case, the Cooper pair is non-local. And there is a length scale. We call it as a coherence length. And it's a psi. And the psi. I'm sorry. And anyway, I will write down naturally by myself. And the psi length scale. Psi length scale is non-local, non-local entity. We call it as a non-local effect. And it is due to the correlation between the two superelectrons. Here we can characterize the superconductor as a dirty limit and a clean limit. And what is the dirty superconductor? Dirty superconductor and clean superconductor. In many superconductor, in the dirty superconductor case, and the penetration depth is greater than the 1500 angstrom. And the clean superconductor, the penetration depth is very small. And in this case, the characteristic of the dirty superconductor is that the short electronic mean prepass and the L mean free pass, short mean prepass in clean superconductor, and the large electronic mean prepass. Mean prepass is that length scale that electron behaves without scattering, and large mean prepass means that the sample is very clean. Therefore, it is naturally understand that the short mean prepass means that there are many imperfections or the later imperfections, and electron scattering is significant, and it is a dirty superconductor. And also the coherence length. Coherence length is the length scale between the two electron correlation in the superconducting Cooper pair. The coherence length here. The coherence length is the length scale of two electronic pairing, and in the dirty superconductor, a short coherence length. We'll write down as psi. And in clean superconductor is a large coherence length. And also in a dirty superconductor, electrodynamics is a local theory. It can describe well the local London theory. But in clean superconductor, the electrodynamics follows the non-local electrodynamics. And in both cases, in the temperature close to Tc, and the superelectron density goes to 0, and the penetration depth diverges. It means that all the sample, entire sample becomes a normal state. In experiment, the temperature dependence of penetration depth follows this kind of behavior. 1 minus T to the 4 lambda L0. Here, T is that the reduced temperature, T over Tc. Tc is a critical temperature of superconducting state. And also lambda L0 is the penetration depth at 0 temperature limit. And here, the temperature dependent penetration depth follows this behavior in the experiment. Experimental relation, not relation, experimental temperature dependence. And to describe the thermodynamic behavior of the penetration depths and coherence lengths, they proposed that two-fluid model, and the two-fluid model assumed that there are two fluid of electrons. One is the normal electron, the other one is the superelectrons. And the two-fluid model referred to the Gothard and Casimir. Gothard and Casimir proposed that the two-fluid model assumes that electrons has two particles. One is the normal electrons plus and the superelectrons. And here I say that London equation do not follow well in experiments, and the penetration depth is underestimate in terms of London theory, and it is due to the non-local effect. I will describe for the basic concept for the non-local effect, and it is proposed the P part. And by the P part, non-local electrodynamics. Physicist P part introduces coherence lengths by proposing the non-local effect of the London equation. And here, because as I said, two electrons couple with each other, and the length scale is about 2L. Let's assume that it is a 2L, and it's a non-locality of the superelectrons. And from the origins, we can denote as R prime from the origin, and at some place we can write down this R. Then in vector relation, vector is that from the origin, from the superelectron at some points, we call it is vector R, and it's R minus R prime. And this superelectron is not a local entity, but it is there is a size, and it is proposed that the non-local effect. And the coherence lengths, they propose that the coherence lengths psi 0 is the characteristic dimension of superelectron, the length scale of the superconducting wave function. Characteristic length of superconducting wave function of superelectrons. And here we denote it is a coherence length. It is a length scale to couple the superelectrons. And we already know that Ohm's law is that the current density is proportional to the electric field. The coefficient is, we call it is electrical conductivity. And P-part non-local generalization of the Ohm's law of Ohm's law, and it is write down as J current density is over the 3 sigma 4 pi L integral dr prime I to the 4, and it is R as a function of R dot E R prime, and also it is exponential minus R over L. Here we know that R is that R minus R prime. In here I do not describe why the P-part generalize this Ohm's law. And anyway, it is not important in detailed expression of this non-local carrier density. Anyway, then we only assume that we can understand that non-local effect is due to the superelectrons have a finite size as coherence length. And from the uncertainty principle at T equal Tc, from the uncertainty principle, and momentum variation is order of kBtc over Vf, because Fermi velocity and the momentum variation has this order, and one electrons within kBt has, because only electrons within the kBtc play a major role in near Tc, and Vf is the Fermi velocity. And from the uncertainty principle, the spatial variation has h bar over delta p, and therefore it can be write down as h bar Vf over kBtc. This is order of the uncertainty, and therefore the coherence length, P-part assume that the coherence length has proportional to this uncertainty region, because he assumed that the superelectrons follows the uncertainty principle, and therefore in coherence length is proportional to the kBtc and A, and it is a proportional constant. It is a numerical constant, and a typical clean superconductor, and the coherence length is very large. I say that in clean superconductor, penetration depth is zero temp. Anyway, it is a zero temperature. Zero temperature penetration depth is very small, and the coherence length is large. It is a clean superconductor, and anyway, then this coherence length plays a role analogous to the mean free path in the normal electrodynamics of a normal metal, and therefore in clean superconductor, psi zero, the coherence length is very large in clean superconductor. By applying magnetic field, the magnetic field has the momentum, and the momentum contribution by the magnetic field, we can interpret it as a vector potential, and on the magnetic field, we can define that the magnetic vector potential, because we assume that equals zero, and here in electrostatics, not electrodynamics, and here canonical momentum can be write down mv plus E over Ca. We can define that the vector potential, and here anyway we can define that magnetic vector potential like this, because and the divergence be always zero, and the curl of divergence should always zero. Therefore, we can define that the magnetic vector potential. And from the Coulomb gauge, we choose that canonical momentum can be write down like this. And in the absence of magnetic field, in the average value of momentum is equal to zero. Therefore, the super electrons, if there is a super electrons expectation value, the average value is like E over mca. It means that super electrons behavior in the opposite direction by inducing the current direction. And for example, and the super electron density is NSEVS, and it is minus NSE square over MC A. In other words, it is A over lambda C, and it means that by applying magnetic field, and we know that the generation of Lenz law and anyway, then for generating magnetic field in this direction, the current direction like this, but from the Lenz law in the superconducting state do not favor to have the increase. Anyway, inside of superconductor, the magnetic field always zero. Therefore, there is a screening current, and the screening current generating and JS in other direction, and the different direction induces opposite magnetic field, and therefore opposite magnetic field, it is applied magnetic field, and the internal superconducting state also generating the negative magnetic field by introducing the negative direction current density, and that is meaning of a negative. And therefore, from the generation of the supercurrent under the limit for the H close to zero, and anyway, this kind of carrier super electrons has the different opposite current, and therefore in the case and Molecular Ohm's law, In the other expression for the non-local current density, P part proposed that the supercurrent as a function of R is that minus sign is important, and 3 over 4 pi psi 0 lambda c and integral dl prime r to the 4 r dot vector potential r prime exponential minus r over psi. In here, and r is that r minus r prime, as I said, and also coherence length is that 1 over psi 0 plus 1 over L. From the, as I said, from the two fluid model, this length scale, characteristic length scale is the super electrons, and this is normal electrons. And the two fluid model consists for the two electrons, normal electrons and the super electrons.